So now we're gonna go seriously on the basic of how to design. Okay, how to design pre-stressed. Okay, so by now you should be able to know, or you should be able to visualize of how pre-stress pre-stress beam, especially beam, the process of casting, the process of how the mechanism of it, the method that they're using, on the site how it's being constructed, at the factory how it's being constructed, the what we call that, and other all the element things that they need, like a tendon, like a jack, anchorage, the wedges. So all that thing you have to have in your mind. That means you already understand that all the part component and so on. Okay, because when you design, you need to know what you design. Okay, and then you need to also able to visualize the location of it, the what we call the component of it. All right. So one thing about pre-stressed design is whereby the first thing you are you have to understand the concept of it. Okay, and please remember the most important thing, not really the most, I mean, the main criteria when you design pre-stress is the pre-stress force, is the force. Okay, the force that you want to apply to the tendon. How much do you want to apply? So that amount of force that you want to apply is the value that you need to find, or you need to calculate, you need to design, you need to know. Okay, so how to know is where it started with this slide. Okay, all right. So this is the outcome for this course, what we expect you to get or to obtain. So definite the limit state. All right, you must be able to definite the limit state. Okay, what are the limit state condition and so on, like we discussed before. Conduct the analysis of section. Okay, discuss the application of the serviceability limit state design for pre-stressed concrete. I think we had done a little bit of it before. Able to determine the minimum section. So what would be the section that you want to propose for your pre-stressed beam? And also lastly, able to calculate the pre-stress force. Okay, so this is one of the main parameter that needed to design pre-stress beam. Okay, so in terms of introduction, we say pre-stressing to maintain favorable stress condition in concrete member under load. So you have to retain the stress, because you already applied the stress, okay, the tension. So if say that you cannot maintain the stress, what will happen? It will move, it will the performance will reduce, and so on. So then you will not be able to get the optimum strength that you require from pre-stress scheme. So therefore, working load considered both maximum and also minimum values. All right, so there must be a range. So normally for pre-stress design, you always play around with the range. You have the what will be the maximum, what will be the minimum. It cannot go lesser than minimum, it cannot go bigger than the maximum. Okay, and primary analysis in the pre-stress is based on service conditions. So service, always remember, it is in for service conditions, service where you have applied the load lah. All right. So when we have like the ultimate limit state, this taken from the class itself. Okay, so generally, because well, we're talking about steel, I mean RC. So the principle or the concept, the material is still the same. We are using concrete and also steel. Okay, but of course, in terms of they are in terms of certain condition, they are a bit different. For example, that in terms of concrete, okay, so in terms of concrete, it's still the same. All right, the properties of the concrete that used in the RC and also that used in steel, sorry, in pre-stress, still the same. All right, so we still have the maximum FCK, the maximum values, okay, of your characteristic compressive strength, at 38 days. Then the design value that you can use for your design is always a bit lower, like 60% of your characteristic compressive strength. Okay, then that one is concrete. Okay, then we have for steel. Okay, all right, where is it? Okay, for steel is a bit different because we focus more on the pre-stressing steel. So when talking about pre-stressing steel, they have like what we call as 0.1 proof stress. So 0.1 proof stress. So for example, like you have the FPK, which is the ultimate tensile strength of your pre-stressing steel. Okay, so then it will be, for your proof stress here is where you're gonna use it. Okay, in terms of what we call after, it's like empirical data. When you do the proof stress testing, like you stress, you release, you stress, you release, you stress, you release, like 100, I think 100 cycle or something, the testing, then you will get how much is the reduction of the stress. So it will reduce. Okay, so this is the values that you're gonna use it for your in your design. So which is your what you call your tensile strength. Okay, after it's a proof stress, yeah, proof stress strength. Okay, so this is where you have these values. Okay, so this is where we measure about 0.1% proof stress and the elongation. So this is where you have the parameter. Okay. Alright, so let's take a look in terms of the notation. Okay, notation and sign convention. So okay, so we have, for example, we have a rectangular section like this. Okay, a basic type of pre-stressed beam. Okay, then you have the width and also the height. Okay, so then normally we have the placement of your tendon. Okay, say that it is placed somewhere there in position, and when you have the top part, we call it as a top fiber. The bottom part, we call it as the bottom fiber. Okay, and you have the YT and also YB. So what is YB? Is the depth of your what we call top depth and also bottom depth. Okay, from the neutral axis. Okay, effective depth lah. Okay, right. So we have elastic section moduli, which is representing by Z, Z, T, and also ZB. ZT for Z top and also ZB for Z bottom. So why you have different top and bottom? Because you have different Y. So therefore your elastic section will also different for the top and also for the bottom. So the equation is I divided by effective depth. Okay, and also you have the E, the eccentricity, taken the position of your tendon from the neutral axis. So as it goes up, if it pass through the neutral axis, then your E is negative. So when it's below neutral axis, your E is positive. Okay. Oh, sorry. Okay, so you have the area, and then you have the compressive stresses, tensile stresses. So it's positive and also negative for tension. So I always hold to this, where you compressive, you compress, so then it's positive. So when you have tensile, then it becomes negative. Okay, because when you compress, then it will elongate the other way. So then it increase the length. But when you tensile, the stress will somehow rather it will pull up, and then you will get it a bit shorter, so that it goes negative. Okay. Alright, so bending stress. So this is the formula we base on. So we have stress equal to minus my over I. Generally lah, okay, it could be my over I. Alright, so we consider, how much stress applied here that cause the beam to bend. So that is basically we call as bending stress. Okay. Alright, so let's take a look what will happen if say that we have pre-stressed beam and it is subjected to axial pre-stress force. So one thing you have to aware, okay, as usual on the beam you have a load, okay, design load. Alright, so you have the P applied. So now we want to know what is actually the value of the P. We don't know how much you can apply or pull the tendon so that you will get the performance as you expected. Okay, so generally you cut the cross section of this beam, section BB. So the first stress that you will consider here will be the stress. Okay, pre-stress means that you apply the P and then you divide by the section area. Okay, so this is where you have the area lah. Okay, then you have it plus. So because there are other stresses beside the stresses caused by the force, okay, by the tendon force. So you have the plus with the m over zt. So what is m over zt? This is bending stress. So remember the bending stress, okay, is equal to my over I, okay, my over I. So generally you can replace by z is equal to I over y. Okay, so therefore then you have it, terbalik lah kat situ. Okay, so you have it for the top will be different, for the bottom also will be different. Okay, for pre-stress it's the same, for top and bottom it's the same, because the formulation doesn't include the y value, so y top and also y bottom. So bending stress you have the y value, so then you have two conditions of top and bottom differently. Okay, so then you equal these total stresses, then you will get the total stress at the top and also total stress at the bottom. Okay, by calculating, by plus the two conditions, means that the PA plus with the M over Z top, then you will have the PA, okay, plus with the MZ to the bottom. So then you have it FP. Okay, alright. So then the total will be FT maximum stress at the top and also maximum stress at the bottom. So top will be compression, bottom will be pressure. Okay, so with that, when you develop the one equation, then you should be able to know that for each of the equation, you have two additional conditions whereby you have top and bottom. Then one more thing, you have the condition of the moment condition. Moment whereby you have two, we say that it has a range, right? Maximum and minimum. So therefore you have moment maximum and also moment minimum. Okay, so for each of it you're gonna have two. So you have top and bottom for maximum moment, for maximum moment. Alright, so then later you will have for top and bottom as well, but you have for moment minimum and also moment minimum. You look at the values of your elastic modular also change. When you have the top, it will be a top. When you have bottom, it will be a bottom. The same goes to the under for maximum moment. So when you have bottom, it will be bottom. When you have top, it will be top. Okay, alright. So next we will see in terms of this equation. So can we calculate the minimum pre-stress force required? Yes, you can calculate the minimum pre-stress force required by considering that there's no tension. So how to consider it? By taking the triangle. So then this is your top stress, this is your bottom stress. So your bottom stress is equal to 0. So it means that your maximum stress will be at the top. Alright, so then you can utilize the formulation, okay, by taking the FB, the bottom stress equal to 0, and the bottom stress is equal to P over A and minus with M maximum divided by CD. So this condition is where you're gonna, what we call that? Okay, so this is where you have the formulation earlier. Okay, then you can simplify it, and because you want to know the pre-stress force value, so you put the pre-stress force at the left side, then everything else is at the right side. So then we can generate one formulation that can calculate what is the minimum pre-stress force required for pre-stress beam. Okay, so then next we have maximum stress in the top. Okay, so when you have it 0, of course you have this as maximum. Okay, because the triangle cannot go furthermore or othermore. So this is the maximum that it can go. Okay, unless you have different conditions, special conditions, so that it will be different case. So with this, basically it generated from this equation as well. Okay, maximum stress. Then you will have your FT, which is your top stress. Okay, top stress. Then how to calculate your top stress, since that your top stress is maximum, is by utilize the formulation here. Okay, generally maximum. Okay, and you will get it because P over A, ZB over ZT, by considering the moment values and also the PA, then you will get your the value of your maximum stress. Okay, so it's already simplified actually, so no need to write your head to figure out how. Okay, so this is the maximum stress and this is the minimum pre-stress force. So please don't get yourself confused. Okay, when we say stress, it could be the symbol of stress. Stress, stress, and also it could also be in the symbol F. Okay, so it's the same. Alright, it's the same. It's still a stress. Okay. So then you have the top, bottom, lah. Okay. Alright, any question before we proceed? Soalan? Ada soalan? Nadia?
No, madam.
Okay. Ilya, are we clear?
Clear, madam.
Alright. Okay. Ashraf, okay? Clear?
Okay, madam.
Okay, alright. Yeah. Okay, so hopefully you can follow that. Very, I think, straightforward lah. Okay, I don't think it's so much fancy. Like I said, after this you will see so many type of formulation that you need to be able to derive and also understand where it comes from so that you understand the behavior of it. Okay, let's take a look first example, shall we? So a simply supported pre-stress beam which is given the size 200 times 300. Okay, we have 6 meter long, right? 200, 300 times 200 is the shape will be a bit boxy sikit lah. Okay, it's a bit boxy sikit. It's not that slender, so it's a bit boxy. Like this. Okay, so you have 250 and also 300 here. Okay, and it says that the beam carry imposed load. This is the imposed load with 8 kilonewton per meter with 0 eccentricity. Okay, so in terms of you, what does it mean when it says 0 eccentricity? Means your tendon. Okay, say that this is your neutral axis. Your tendon is exactly at the center of it. Okay, so then it doesn't have any eccentricity because the load will be applied here lah. Okay, actually the concept is more or less the same with column. Okay, where you have this column. Okay, and then you apply, you have it x and y, then you apply it here, then you have axial load applied. Okay, it's just matter of for column you have to lay it horizontally to get the behavior. Okay, so determine minimum pre-stress force required and stress at the bottom fiber under moment maximum. Okay, so when you look into this equation, it's actually very straightforward. It's nothing fancy about it. Alright, so it's very straightforward. Whereby here we have self weight of the beam. So self weight we can also use 25. Because I know some of you like to use 25. It really depends. Doesn't matter about that. Then you have total load. Total load include the self weight plus 8. 8 will be the imposed load given here in the question. So you have more or less the total numbers of your, what you call that, of the loading. Okay. Then you have the moment maximum. Moment maximum where you consider the amount of UDL. Okay, multiply with L squared divided by 8. Okay, so then you have the values of your area and also section modulus dB on ZT, which is you conclude we have square over 6, and total up you will get like around 3.75 minus 10 power of 6. Okay, so then this is the amount of section modulus that you're going to use. So since that in this case, okay, it's equal. Because why it is equal? Due to the okay. Okay, so okay. Alright, so section modulus, if you look into here, your bottom is equal to your bottom is equal to your top. Okay, so you have ZB equal to CT. Why? One of the reason because of symmetrical. Your neutral axis is somewhere here. So your top height is equal to your bottom height of your effective depth. Okay, if not effective depth, effective height. Alright, so you have DH square over 6. You can multiply, use all the, what we call that, ingredients. Okay, you put it, you kind of like CB of equal to CT. Okay, if like we say, if your effective that top and bottom is not the same, so then your ZB is not equal. But if say that the top and bottom is the same, so then you will have it. Okay, so yeah. Okay. Can I erase? Okay. Alright, so you have, then you have BH square over 6. You can check the formulation to calculate the modulus in your solid mechanics book actually. Okay, you done this before, probably you forgot already, so it's good time to recall. And then you have your section modulus, okay, section modulus. And you have here is equal to P, which is the force, okay, the pre-stress force is calculated by, you have your M maximum multiplied with area divided by CB. So why is this? Is where you consider that there's no tension. Okay, because what you want to determine here is the minimum pre-stress force. So how you want to detect the minimum pre-stress force is by considering your tension force is equal, tension stress is equal to 0. Okay, the bottom part of your stress is equal to 0. So then you calculate, you put it inside your moment maximum area and also divide by C, and you will get the value of 88.67 for your pre-stress force, yeah, based on moment maximum, yeah, pre-stress force. Then you have your stress at the top and also stress at the top, because your stress bottom is equal to 0. So the maximum stress is where you can calculate P over A, ZB minus plus with the ZP. So this is the values, and you calculate all, then you will get the total of your stress at the top. Okay, alright. Any questions, soalan? Soalan? Anyone?
No question, madam.
Okay.
No, madam.
Tak ada? Anis, tak ada question?
Tak ada, madam.
Alright. So clear, I hope you guys clear in terms of the formulation, because this is just the beginning. This is just the beginning of your calculation, the design part. So you will see lots of other equation later on. But the basis of in terms of the how you form the equation is coming from this slide. Okay, it comes from this slide. So you need to understand this slide. Okay, you need to understand the stress coming from the bending, because this is FT. Here are the total stress. The total stress for maximum and minimum top to the bottom, top and bottom. Okay, so then you have this one is the stress coming from the tendon to the tendon, which is the tension stress. And then you have the bending stress, so plus we have two different stress. So total up, you're gonna get the FT, which is the maximum stress, okay, or the optimum stress for top and also bottom. Okay, so I think I will stop here first, because the previous group stopped here. So if I proceed, then it will be difficult for me when you guys didn't do the lecture, the same content. Okay. yang because the group D tu, the morning lecture I have some difficulties in terms of sharing the video. So then we just had the discussion. So then last week we proceed with the first lecture, the technology of pre-stressing that I've shown to you earlier. So I have give the lecture to group D last week. So then therefore they have a slot of presentation this week and also half of the chapter of today lesson. Okay, so I think I will stop here as well for your group. Okay, and we're gonna continue with when the member is subjected to eccentric pre-stress force. Means that your tendon is not placed exactly at the neutral axis. Before this, you assume that your pre-stress, tendon is placed exactly at the neutral axis. So therefore, called axial means your E is equal to 0. There's no eccentric at all. Okay, so when you want to consider eccentric, whereby you are considering there are distance between neutral axis to the position of where you locate your tendon. Okay, so that is called eccentric. So it could be below positive eccentric, above minus eccentric. Okay, so it will be members subjected to eccentric pre-stress force. So means that there will be a distance between the location of the tendon to the neutral axis. So let's take a look on the beam. So the formation of the beam is still the same, still like a rectangular beam. So you have a UDL on it. The only difference will be the position of the P. Okay, the position of the tendon, which give you a slight distance, of the what's my okay, all right, which is you will see the E, right, the eccentric position of your tendon, right? So then you have the cross section of it with the stress distribution of the P, where I give you the P over A, which is your what we call that, pre-stress force. Okay, pre-stress, not pre-stress force, the stress coming from the force, okay, towards to the perpendicular to the area of your beam section, plus with the values coming from the bending. Okay, the bending stress along the length of the beam caused by the UDL, or the load applied along the beam. Okay, and plus also we have another additional of a stress which is coming from the eccentric, the position of the tendon. So the position of the tendon, basically it give you P multiplied with E. Alright, so P multiplied with E is actually equivalent to moment. Alright, so moment. So if you look into this equation and this equation, is actually the same equation, which is both representing the bending stress. So one bending stress is caused by the UDL, which is the load applied along the beam length, and then another one will be due to the moment that caused by the position of the tendon, which is multiplied with the eccentric. So both bending stress will be add up, total up, then you will have the equivalent of total stress for the top fiber and also for the bottom fiber. Okay, so that is kind of like what will be the stresses, the total stress that you will have when you have your P, which is, not exactly at neutral axis, which is a bit below the eccentric, means at neutral axis, means give you the eccentricity. Okay, so if you look into here, you will have the equation when you have the line of your stress triangle. Okay, whatever goes this way is positive, whatever goes this way is negative. So you will have this one is negative, this one is positive. All right, and when you want to have the total of the stress, for example, you have the top stress or FT. So when you write the equation, you will get P over A. Then you have plus with M over ZT. Then you have minus. This is minus with PE over ZT, which is this equivalent to bottom stress. Okay. So when you have top stress, sorry. When you have bottom stress, you will write the same equation but with a different notation, which is you have P over A, then you have minus M over ZB plus, because it's going to that direction to the right, plus with PE over ZB, which is equal to bottom stress. There it goes. Okay, tiba-tiba hilang. Okay, alright. So yeah, and we have the total stress of top and also bottom. Okay, so with this, then we can conclude the two equation of your stresses. Okay, my internet line not so smoothly. I don't know why. Okay. Alright. So with the two equation for the top and bottom, so we know that for the moment value, you have the value of moment maximum and also moment minimum. Okay, for each of the top and also bottom stresses. So then we will end up with four equations for moment maximum, moment minimum, top and also bottom. Okay, top stress and also bottom stress. So the same, same what we had for axial stress or axial position of your tendon. Okay, where we can calculate the critical condition for tension, which is we say that there's no tension. So when there's no tension, we can say that your bottom stress is equal to 0, which is no tension. Then we can equate the values of your minimum pre-stress force. So minimum pre-stress force is equal to M maximum, moment maximum, divided by ZB over A plus with E, eccentricity. So this will give you minimum pre-stress force. Okay, so with minimum pre-stress value, you can evaluate what will be your maximum stress. So you can include your minimum pre-stress force in the equation, then you can evaluate what will be your top stress or maximum stress. Okay, so for example, in this example of 2.0, alright, 2.0, we have the rectangular beam 150 multiplied 300. Okay, so it's a simply supported beam over a 4-meter span, and we had then the beam is supporting live load of 10 kilometer per meter. So if a straight tendon provided at eccentricity of 65 mm below neutral axis and centroid of section neutral axis, find the minimum pre-stress force necessary for no tension, okay, live load at mid-span. So you have, like, when we say that minimum pre-stress force means we say we want to find P not minimum. No tension means that your FB is equal to 0, and we have the live load at mid-span means the condition is moment maximum. So calculate the corresponding stresses under self-weight only. Okay, only at mid-span and also at the end of the member. So there are conditions. Yeah? Okay, later on we will look into it. So the beam properties we can see here, we can calculate what is the self weight of the beam, which is the area, the cross section area of the beam, 300 multiplied with 150 multiply with the density. Density, some of you guys use when you use Eurocode, the new one you have 25, so you can adjust that. So the value of your self weight calculated is 1.08. So this is the area. Then the section moduli says that it is what we call a rectangular section, and this is symmetry. So then your top section is equivalent to the bottom section, which is to give you BH square over 6, and you have the 2.25 multiplied with 10 over 6. Okay. So with this, basically you will have a condition of moment maximum and also moment minimum. So what is moment maximum and what is moment minimum? So moment maximum is whereby you will have consideration of your self weight plus with your dead load, means that any UDL, plus with your imposed load. So this will give you the value of moment maximum. While moment minimum, you only consider the self weight only. So that one, that will give you the value of your moment minimum. Okay. So okay, sorry for that. All right. So we have the calculate. Then after that, we calculate the moment maximum and also moment minimum. So you have each value for the value, and then we can calculate for top and also bottom. Okay. So with this, then we can estimate what will be the minimum pre-stress force. So by taking minimum pre-stress force is where we consider FB is equal to 0. So under moment maximum, because the question purposely asks you, to calculate minimum pre-stress force for moment maximum. So you will take the value of moment maximum, all right, and you will have the value of P minimum, which is given calculate 193 kilonewton. Okay, so later on in your formative assessment, I will take the I think you can recalculate right this equation. All right, so calculate stresses at mid span under M minimum. So for M minimum, so then you have already the values of your P. Okay, so your P values, then you can use the P minimum values in the equation. Then you can estimate what will be the stresses for the top and also bottom, where you use the moment minimum. So here you will use moment minimum, then you will calculate your top and bottom. So if you look into the equation, basically since that is a symmetric section, so your ZT and ZB is actually the same. So your equation here and here is actually the same values. I mean, it's just a matter of the change of your plus, minus, minus, plus will be different. Okay, so therefore it's sometimes it's good to calculate like this, so then you will get the values for each of these equation. Then you can just plug in into the whole equation by by using plus or minus operator. Okay, then you get the value for each top and bottom. Okay, so here if you look here, one of the obvious condition that you have to aware is where under moment minimum, okay, where the beam or pre-stress beam only carry its own self weight, the value is negative, right? The value is negative. So when you get the value of negative, basically you will um, aware that the beam is actually experiencing what we call as hogging behavior. Okay, means that it will hog like this. Okay, it will concave like that. So it shows that where the top fiber will concave like that. So as it is initial stress, Okay, sorry, excuse me about that. Ada some people come to the office. All right, so we continue. So the behavior of the beam, because of the what we call that minimum, moment minimum means that the beam carry its own self weight. So it doesn't have any UDL on the top or imposed load on the top of the beam yet. So basically, what will happen when you pull the tendon? Okay, you pull the tendon, apply force to it, then the beam will concave. All right, the beam will concave, will hop. All right, so then we will say that the maximum, the critical condition for the top of the beam will be tension and the bottom part will be compression. Okay, and this particularly so as the initial transfer of prestressed force to the unloaded beam. Okay, so because the beam is not yet loaded. So the E, so that one is when at mid span. Okay, we calculate it when the condition is at mid span. Okay, all right. So when at the end span, okay, and at span, so we consider that the moment is equal to 0 because the question asks you to calculate what is will be the stresses at top and also bottom when the at the mid span for moment minimum and also at the end of the span. So at the end of the span, when we say it's a simply supported, generally it will be like this. So here whereby m is equal to 0, m is equal to 0, and at the mid span will be m maximum. Okay, simply supported, yeah. I think the behavior, you guys familiar with it. So then here, in the case of when you have m is equal to 0, so basically these values will all equal to 0. So then you will end up with only two values, and I give you minus 1.3 and also 9.9. Okay, so that will be your stress at the end of your beam. So the same thing, if you have a beam which is not simply supported, you have cantilever or you have continuous beam. So then you must get the envelope bending moment of the whole length of your beam. Okay, so then you have the stresses for each point, and then you can get the analysis of the along the length of the beam to know the behavior of your pre-stress. Okay, so yeah, that is about it.